All right, so welcome. We are in Chapter 2, Section 4, and let's recap some of the things that we've learned so far. So we have learned how to solve differential equations by using a method of separation of variables. In the last section, we learned how to solve linear first-order differential equations. We now are going to learn how to solve another type of differential equation of what we call an exact equation. Okay? Let me go ahead and give a full disclaimer that you need to have at least a cursory understanding of partial derivatives before you can do this section. So I understand completely that partial derivatives is a topic that you would have learned in Calc 3, and for some strange reason that baffles me, the powers that be have made differential equations only prerequisite is Calculus 2. Again, I don't know who develops the curriculum. I do wonder if they have studied mathematics, but nevertheless, here we are. So we do need, you need at least a decent understanding of how to take a partial derivative to understand this section. So if you need to, either in the announcement section of Canvas, I have linked a video on partial derivatives that I did for Calc 3. If you'd like to start there and then come back. But let's go ahead and jump in. So let's recall the idea of a level curve, right? So notice that now we have a multivariable function, right? And we don't just have f of x, we have f of xy. And if you recall that if your multivariable function was equal to a constant, we would label that a level curve. And the best way that I can try to explain that to you is let's just take a look at the following region here. So based on this map, if you live in this longitude or latitude, or this longitude, latitude, or here, or this, or here, you're looking at 70-degree weather. So every xy, or here, longitude, latitude, is equal to the same c that is 70 degrees. So that's what we mean by level curves. Now, to get to exact equations, well, first off, let's get to a differential equation, and then we'll get to an exact differential equation. But really what we're going to do is, this won't take very long, but what we're going to do is we're going to take the derivative of both sides of this level curve with respect to x, okay? And now, you recall that if you take the derivative of a multivariable function, you would have partial derivatives, right? And of course, the derivative of the right side is just 0. So what you would end up with is the partial of f with respect to x plus the partial of f with respect to y. Now, because we took the derivative with respect to x, you remember that would be implicit differentiation. If there's a y variable somewhere in here, and you took the derivative of a y variable with respect to an x variable, you would have to have that dy dx, right? That it is implicit differentiation. Now, of course, the derivative of c, which is just some constant like 70, is just equal to 0. Now what we're going to do at this point is just solve for dy dx. So dy dx is, I'll do this in one swoop. I'm going to grab this term, bring it to the right side so that it'll become negative, and then I'll divide both sides by the following term. So dy dx is equal to negative partial of f with respect to x divided by, that's not a 2, I'm trying my best here, negative, or just the partial of f with respect to y. Okay. So we've solved for dy dx, and what we would need now is, if you wanted to know the slope, right, then at this stage you could plug in. So that would be one way of finding the derivative of such a function. But remember, our goal is going to be able to solve the differential equation. So what we're going to do to make this a little bit easier, we're going to go back here. Okay, bear with me here. Let's go back to this part right here where we started. And what we're going to do is we're going to try to separate these variables out, okay? So we're going to multiply both sides by dx. So what would that look like? So that would just simply be the partial of f with respect to x dx plus the partial of f with respect to y dy. And then, of course, if you multiply dx times 0, you're still at 0, right? So distributing the dx would cancel this dx here. And now we have our partial, the partials with respect to x and y attached to dx and dy. And now, if you recall from Calc 3, you have actually seen, if you're like, that looks familiar, because that is what we call the total differential of f. Right. So that's the total differential f. Now, the only thing that that we're going to do is what your textbook does, is instead of using this partial of f with respect to x notation, we're going to redefine the we're going to redefine, so henceforward the partial of f with respect to x, we're going to call it something else to make it easier. The partial of f with respect to y, we're going to call it something else to make it easier, to make it nice and neat. So we're going to label partial of f with respect to x, we're just going to label that m. And the partial of f with respect to y, we're going to label that n. Just please understand that this is a function of xy. This is a function of xy. Okay? So now that we've relabeled, let's just plug in. And then we'll be where we want to be. So this is going to be m of xy times dx plus n of xy dy is equal to 0. Now, if your differential equation takes the following form, the solution to these types of differential equations are level curves. Okay, so just understand that. Remember, we want to be able to solve this, so we want to be able to say, f of xy equals, and I'm just letting you know that if your differential equation looks like what the form that I have above, the solution to such a differential equation is itself a level curve. Okay? So let's do the following. Let me give you, we're gonna do it this way. So let's jump into an example. So dy dx is equal to, let's go ahead and write it as negative 2xy squared plus 1 over 2x squared y. And we want to solve the differential equation. Okay, so again, let's fast forward. Maybe you're thinking, is this separable? Is this linear? Is this exact? Well, this is going to be our definition that we'll get to in just a little bit of an exact differential equation. But here's what I'm going to do right now. First, let's just practice. This is an exact equation, but let's practice getting it in that exact. Let's practice going from here. In other words, let's practice going from its current form to the following form. Okay? So, can we make it look like the following form? So let's practice that first, and then what I'm going to do is I'm going to cheat, and I'm going to give you the answer. And then we're going to just test it and show that that how we would know that it is indeed the true answer. Okay? So in the next videos, I will go through the how-to part of getting that answer. But right now, let's just write it in the correct form. So, all right, so this is not bad. I mean, I can just simply, to make things easy, what we're going to be doing is we're going to be moving, some things around since this is a fraction. So you can just cross-multiply. You can think about it as cross-multiplying, dividing, if you'd like to think of it that way. But you're cross-multiplying and you're setting it equal to 0. That is how we'll get it to its proper form, right? So that's going to end up being 2xy squared plus 1. If we cross-multiply, that's going to be attached to dx. And then what we'll have is the negative has to go somewhere, right? So we'll just leave the negative with the numerator. In this case, we'll just leave it in the denominator. So that's negative 2x squared y dy. Okay, so my apologies. So that's equal to negative 2x squared y. So let me kind of go over what I just did, since I got distracted, which I do, by the way. Without your faces in front of me, I get distracted and start daydreaming about stuff. Ready? So cross multiply. So we'll multiply numerator times denominator, numerator times denominator. I just left this negative symbol with the denominator because it doesn't really matter, because what I'm about to notice that the current form still doesn't look like the exact different form of differential equation. So, but it needs to be set equal to 0. So I'm just going to grab this and bring it back to the other side so that this is set equal to 0. Okay, so we're just going to grab this, we're going to drag and drop, bring it over here, and then we have 2xy squared plus 1 dx plus 2x squared y dy, and that is equal to 0. So now we have the form of an exact differential equation. So, okay, so it's at this stage that you would start the process of solving it. But remember what I said. So I'm going to cheat by giving you the solution. And here it is. The solution to that exact differential equation is the following: x squared y squared plus x. So here is, we didn't have to work for it at all, but here's the solution. And for the remainder of this video, the only thing that I want to do is show you how you can rest assured that this is the solution to that differential equation. And to do that, to show it, well, let's just say you just take the partial derivatives, right? So so we're gonna come up here and take the partial derivatives of this guy. So let's take partials. And at the bare minimum, even if you've had Calc 3, at least this will be a refresher. So if we take the partial with respect to x, and we take the partial with respect to y. So now what we're going to do is we want to make sure that you can kind of think of it as, I'm going to take the partial of m dx with respect to x. So take the partial of m xy with respect to x, and then take the partial of n xy with respect to y. Ready? So let's go ahead and do that. So let's start with the partial with respect to x. Ready? So if you take the partial of 2xy squared plus 1, treating y as if it were a constant, right? We hold y as a constant. Let's go ahead and take that derivative with respect to x. Well, the derivative, wait, let me see here. Did I? No, my sincere apologies. I want my sincere apologies. I'm jumping ahead. I'm thinking about if we were going into solving it. What I just did, but when the next video will make sense why I messed up and said the things that I set up. I just want to take the derivative of this with respect to x and the derivative of this with respect to y. So, because I've cheated, I've given you the answer. So let's do that. So if we take the partial with respect to x, we're going to hold y as if it were a constant. So that's easy. So the derivative of x squared is just 2x, and we're just going to treat the y as a constant. So that's just going to be 2xy squared, and of course the derivative of x is just 1, so that's plus 1. And now let's take the partial of that answer with respect to y. So now we'll treat x as if it were a constant. Well, likewise, derivative of y squared is 2y. So that's 2y. And then we will leave the x squared alone because we're treating it as if it were a constant. And of course, if x is a constant and you take the derivative of a constant, that's just going to equal 0. All right. So now, how do I know that what I did was correct? And think of it, you got this is your proposed solution, you took your partials. Notice how this matches what we had, right? Notice that this matches exactly what it was that we had for m and n. So we know that that is the solution to that differential equation. Now, let me be honest. There's quite, to actually go through and show that it's quite a lot more going on here. But I'm not gonna go through. I'm not gonna go into that for right now. Let's go ahead and take a break, and when we get back, we'll define exact differential form, and we're gonna do two things. We want to come up with a test for exactness, right? Wouldn't it be nice to know, if you're trying to solve a differential equation like this, wouldn't it be nice to know that it is exact before you start doing a bunch of operations? So we want to know how to test to see if it's exact, and then if it is, we need to know how to solve them. So that's where we will begin when we get back.